我也是4号才找到，不可能他会自己。我这个第一根之前
就前年之后我都喜欢我看什么？
没有，就几个4个3个，看多长时间的。
课就不要我们重复这样。
还有人挂的吗？
你想做什么？先说文章，完了文章，你先说文章，完了文章以后会，
Oh, okay. I like it. Yes, I want that. What?
简单一点，我也知道。
Yes. No, not at all. Just too.
Oh,
But no issue was like, you know, have a prior heat map, like one, one data point. Like, confused about how to
Pretty much all the certifications speak about those.
That we got.
It's the same map, actually. I look at the book.
Yeah, it was like after this. Yeah, just going some different standards.
Yeah.
I guess so. But from here, like, have you seen like chunks? We're definitely doing. We started. That's like no, where you put your knees on your present.
Good afternoon, everyone. I think we should start. All right, so like not many people. Have you already started with your fall break?
Yes, sir.
I heard some requests for the extension of your homework 2 to be after the fall break. And I'm not sure how many of you really want this extension because my original thinking is that I don't want to sacrifice I don't want to ruin your travel flying in fall break. So my current response is I need to wait for many. I need to count how many requests I received. If there are a lot of many, the majority. Yeah. No, not deliver release of homework 3. I mean the submission of homework 2.
No, like, are you planning to release homework 3 like soon or?
No. I mean homework 3 will definitely be released after fall break.
Okay.
I mean homework 2. Because the original deadline for homework 2 is this Saturday, right? And it's right before the fall break. I mean, I have received a few requests and asking possibility to extend it after the fall break. But I'm not sure if it's like the majority or most of you want to sit in your home to finish homework 2 during the fall break. I thought most people won't do that. But that depends. If everybody loves to do that, I'm happy to offer an extension. If not. But anyway, like if you really want an extension, let me know. Otherwise, I just consider like just a few requests. I cannot do that. Otherwise, it won't be fair for hardworking students, right? Okay, so let's continue with the probabilistic graphing models. So in the last lecture, we have introduced how we construct a directed graphing model. It's called a Bayesian network, right? And a Bayesian network is essentially a cyclic directed graph. And we consider an important problem is that given a complicated Bayesian network, how can we answer probabilistic queries like giving you an arbitrary non-intersecting sets of nodes A, B, and C. So A, B, and C are three groups of the variables. They're non-overlapping with each other. And we want to test the conditional independence that whether given the nodes in C are observed, A and B are independent or not. And this is our problem. This is actually the key problem to analyze your Bayesian network. So to answer this question, we have discussed 3 basic cases. So if you still have a question, we consider the special case that we only have 3 random variables, A, B, and C, right? And we consider 3 basic cases. One is like tail to tail. So tail means we look at the nodes which are conditioned on, not in C, right? So if the links or edges meet at C with all their tails, It's called tail to tail. And the second basic case is a head to tail. So basically, we have like A, C, and B. We have something like this. So the head, the C is conditioned on, right? So is observed, and the edges meet at C with one head, one tail. Or reversely, you can do this. Okay. So in both cases, this is a head to tail. In both cases, we can conclude that given C observed, A and B are condition independent. But if C is not observed, meaning that when condition are nothing, we usually cannot conclude that A and B are independent. And I'm showing that with this rule. But we have a very important case, the third case, which is a little odd, is called a head-to-head. So basically, if your C connecting to A and B like this, the C serves as the parents. Oh, sorry. This is over here. So this is A and this is B. A and B serve as parents, and C is the children. This is called a head-to-head. Head-to-head, and the arrows meet at C with their heads. So in this case, the conclusion is opposite to the conclusions we have obtained for tail to tail and head to tail. Right? So basically, in this case, when C is observed, we cannot say A and B are conditionally independent. So basically, when C is observed, that A and B are dependent. But when C is not observed, meaning that when conditioned on nothing, A and B are independent. So this is contradictory to the tail to tail and head to tail case. So with the three basic, and remember, when we explain this head structure, we introduced an important effect called explain away effect, right? So it's about like using an example with your vehicle, your electrical gauge rate and tank status, fuel tank status, and battery status, right? And this case can be generalized into that given C or any descendants of C observed, A and B are dependent or not independent. Only when C and all its descendants are not observed, A and B are independent. So it's kind of like subtle, but this is a way how Bayesian network works. And given these three basic cases, we introduce the deseparation algorithm. Sometimes it's referred to as baseball algorithm. So we can use the graph traversal type algorithms to test whether given an arbitrary set of random variable C, whether A and B are conditionally independent or not. How can we do that? We just enumerate every path from any node in A to any node in B, right? So given some particular path, we look into every node in this path. If any node in this path satisfies the following conditions, then you can claim that this path is blocked. Then we switch to another path to look into it. So what kind of three situations we need to test whether this node satisfies or not? Right? First, whether this node has the arrows meeting at it with head to tail or tail to tail. At the same time, this node should be inside C. Then you can claim, okay, this path is blocked. So why it's called baseball? You can consider your global ball following this path, right? So if you have some node in C at the same time, the arrows meet at this node with head to tail or tail to tail, you can consider there's a rock in a a path. So when you throw the ball, it just bounces back to this block. Or a third case that this node or any of its descendants is not in sync. At the same time, the paths or the edges meet this node with head-to-head case. It's kind of contradictory. It's different, right? You must, if the edges meet at this node with head-to-head, you must ensure that this node and any of its descendants are not in sync. Then you can also conclude that this path has already been blocked, and you need to switch to another path to do the check. If every possible path from one node in A to another in B is blocked, and you can safely conclude that A and B are independent given C or conditional C, right? In any of the paths, they are not blocked, meaning that when you throw a ball, you don't meet any walls or rocks, you will successfully arrive at B, yeah. And then you just quit and say, okay, A and B are not independent given C. So just enumerating and checking procedure. So this is called D-separation feasible error. And then we have gone through like 2 examples. I won't repeat it again. So now let us look at the another important concept called Markov-Blanket. So what is Markov-Blanket? Markov-Blanket can be considered as the minimum subset of random variables which separate one particular variable from the remaining variables. So given the Markov-Blanket of a particular random variable, we can conclude that the particular random variable is independent to all the remaining random variables. This is the concept of the Markov-Blanket. So intuitively, you can consider it's like a firewall. It's a firewall that separates you from others, and meaning that given this firewall, you are independent to all the variables outside the firewall. Now, how can we determine your Markov-Blanket? How can we determine it? An idea?
The marginal?
Yeah, that's one way, right? An idea? So the basic idea follows the same as you. We just look at the conditional probability. We look at the conditional probability of xi given all the remaining random variables. So if we can find out a partition of the remaining variables, so those are all xj's which are not equal to I, so we can find out a partition, meaning that this remaining set of random variables can be written as A union with B, right? A and B are 2 subsets of random variables, and their union is all the remaining variables excluding xi. If we can show that this one equals to the conditional probability of xi given A, then A is the Markov-Blanket, right? Because this is equal to xi given A and B, right? The definition of conditional independence. Given A, B, and xi are independent. Now let us look at how can we determine A from the definition. So the conditional probability is equal to the drawn probability of all the big D variables in your Bayesian network, and divided by the marginal distribution with xi marginalized out, right? Is it right? Everybody is comfortable at this point, right? And then we can look into our network structure, right? So given Bayesian network, of course you can, like if you don't have any assumption, like you can expand your drawn probability with Bayes rule, right? But with some Bayesian network structure, your drawn probability can be written as a product of a set of conditional probabilities, right? So like this is x1, this is x2, x3, and you have a x4, x5, something like that, right? So basically, your joint probability, according to this network structure, it can be decomposed as a product of the conditional probability. Of course, for the root node, you don't have any parents. That means your parent part is just empty. So we can write down the joint probability this way, and similarly, in the marginalization in the denominator, we just marginalize this product over xi. Right? So now you can imagine what kind of variables can be cancelled from the numerator and denominator. Consider, right? Think of it. Those variables, if they can be cancelled from both the numerator and the denominator, they are not variables in the Markov blanket, right? They are something in B. Right? Yeah. Yeah. So then we consider we want to ask what kind of variables should belong to A according to this fraction, right? What kind of variables should belong to A? Those variables which cannot be cancelled from the numerator and the denominator, right? Then which set of variables cannot be cancelled?
The conditional if he has dx xi in his formula, it can be cancelled. Then if not, he don't contain the xi, the integral can become 1.
Yeah, exactly. Right. So basically, if any variable, it is coupled with xi, it cannot be cancelled. Why? Because we're going to integrate over xi in the denominator. They're coupled together, we cannot cancel it. But for all the other variables, has nothing to do with xi, then they can be cancelled. They must belong to B, right? And then let us look into which set of variables will be coupled with xi. You can look into all the conditional terms, right? If xi appears in some conditional probability, which positions it can be? This is just one case, right? Xi appears in the probability, right? But there is also some case that xi appears in the parent, the part which is conditioned on. For example, x1, right? So I equals 1, then the conditional probability that x1 given, say, x2, x3, or x2 given x1, x3. These two conditional terms, all the remaining variables must be coupled with x1. Right? In the first case, x1 appears in the probability part. It's not on the conditional part. Then all its parents will be coupled with x1. Why? Because in the denominator, you need to integrate our xi, right? So it cannot be cancelled. If x1 appears in the conditional part, then all the remaining variables, x2, x3, whether it is inside the conditional part or not, they must be coupled with x1 as well. Because we're going to integrate over xi, right? So they cannot be cancelled. But for all the other variables which do not co-occur with x1 in some conditional part, in some conditional term, then they're just free. You can factor out from both the numerator and the denominator. Does it make sense? This is just some calculation trick. Right? If you want to do this is the marginalization, right? So all the terms which contain xi, they are coupled. That means all the variables in such kind of terms are coupled together. They cannot be cancelled. But all the terms which do not contain xi can be factored out. Right? And those ones are cancelled with the corresponding terms in the numerator. That's the key idea. So if you still feel confusing about that, write down some specific Bayesian network and do this division. It will be much more clear. That gives you the high-level idea. Okay. And then Markov blanket for xi, it includes xi's parents. Why? Because when xi appears in the non-conditional part, all the conditional part will be coupled with xi. They are in the same conditional term. Right? Xi's children, because something conditional xi and something others, this one is coupled with xi. And also the children's co-parents. Right? This is the children. This is the children. And xi is one parent, and there could also be other parents as well. So this and xi are coupled as well. So those three sets of variables form the Markov blanket of xi. Does it make sense? Okay. So to give a bigger, here's, suppose this is xi. We'll look into its Markov blanket. We'll look at its parents here, right? So you can imagine, because those parents are coupled with some conditional part like this. Okay. According to the definition of Bayesian network. And its children here and here, right? And its co-parents here and here. Why? Because these children and co-parents will appear, we denote this as like x bar, give me xi, and its co-parent, right? And this part, say x tilde, it will be contained in a conditional probability x tilde given xi and co-parent. So both x tilde and its co-parent are related to x tilde, are related to the xi. So it must be in the Markov blanket. Any question? Everybody's comfortable?
So these are all of the nodes that xi is dependent on.
Yes. Well, like more rigorous speaking, xi, Markov blanket, or in other words, like you can see it's dependent, but it's not very rigorous. But basically, I say, okay, no matter how large this network is, like given all those shaded nodes, xi are independent to all the remaining variables in the network.
Okay.
Any other question? Yeah, again, like if you feel like a little uncomfortable with this abstractive illustration, you can just write down, say, this simple network, and write down the factorization of your joint probability, and to do this, you will find the Markov blanket of, say, x2, or x1, or x4, x5, whatever. And you'll know why the Markov blanket is defined that way. Does it make sense? Okay. So here we have introduced the basics of the Bayesian network, right? And basically, Bayesian networks are constructed according to the factorization of your joint probability. And if you put some assumption, your simplified assumption over the condition probabilities, you have a simplified structure. If you don't have any assumption over your joint probability, I mean the factorization of joint probability, then your Bayesian network is fully connected. If you have some assumption over that, then the structure is much simplified. But the issue is that when we determine whether some set of variables are conditionally independent to another set of variables, using deseparation algorithm is still a bit subtle, right? We need to consider the directionality of your arrows. This weird head-to-head and tail-to-tail will end up with totally different results. Right? So therefore, we naturally want to ask, can we have an easier graphical representation of our joint probabilities such that we only based on paths without considering arrow directions, right? Because when we consider arrow directions, things becomes more subtle, more complicated. Right? Is there like an easier way to represent our probabilities? That comes the Markov random fields. So Markov random fields are undirected graphical models. So basically, we represent our joint probability or probabilistic models with undirected graphs. We do not have to consider the directionality of your arrows because there's no directionality. And even better, when we test the conditional independence, we only need to look at the paths. Right? So given A and B, if we want to say whether they are conditionally independent given C, we just look into all the paths from any node in A and node in B. If every path is blocked by subnode in C, then we can claim that A and B are conditionally independent given C. This is much more straightforward, right? We do not need to consider whether this is tail to tail or head to tail or head to head. That's heading. And also the Markov blanket definition for Markov random field is more straightforward as well, because the Markov blanket is simply the neighboring nodes of our interest node. So basically, if I want to know the Markov blanket for this particular node, we just take out all of its neighbors. So it's easier, right? It's easier. In the directed graphical models, like Bayesian error, we need to consider some co-parents, right? But here we do not consider. We just look at the neighboring. So far, NY is good. Error is good, right? Okay, so let us look at how we define a joint probability on some undirected graphs.
Why are the coparents not included in the Markov random fields?
It's just not included. According to the definition, you will see it won't be included. If you use like Bayesian networking, because your joint probability is factorized according to the structure, right? So you must consider the coparents. But here, if you use undirected graphs, there's no concept about parents. Now that there's no parents, how do you see like co-parents? But you'll see like after we define some joint probability over the graphs, naturally you can derive the conditional independence is obtained by looking at this path, purely by path, or the Markov blanket is obtained by just taking out the neighboring nodes. So, if you want to define a probability distribution over a Markov random field, or in other words, an undirected graph, we need to look at the cliques. So, what's the clique? What's the clique? What? Yeah, of course, it's grouping of nodes, but what kind of properties a clique should satisfy? You're parallelized connected. It's not like connected does not mean like something like this. So this node and this node are connected, but they do not belong to a clique because there is no direct edge between the first node and the second node. Clique is more like restrictive and it asks that for any pair of the nodes in this subset, there must be an edge between them. Right? So, for example, those red nodes and edges represent our undirected graph. And this green circle represents one clique because it only contains two nodes, x1 and x2, and there's an edge between them, right? But this is not maximum clique. What is maximum clique? was not 4. Maximum clique means that, okay, if I add any node into this clique, then it won't be a clique. So we can take a look at this, the 3 nodes circled by this blue lines, right? So x2, x3, x4. First, is it a clique? It's a clique, right? Between every pair of edge is an edge. Between every pair of nodes is an edge, right? But is it maximum clique? We can see whether we can add one more node, right? If we add one more node, x1, if it's still a clique, we require between any node and x1 there's an edge. But between x1 and x4, there's no edge. That means if you add x1 into this clique, it will not be clique anymore. That's why it's called maximum clique. This is a concept from the graph theory. So I assume everybody have heard them before. So we define our joint distribution, joint probability over an undirected graph as a product of the potential function over each maximum clique. So basically, we're going to define a function over the variables in each maximal clique. In other words, over the nodes. Remember, each node corresponds to one random variable, right? So for each maximum clique, we're going to assign a potential function over that set of nodes in that clique. And then we multiply all the potential functions together, we normalize it, we obtain our joint distribution of the undirected graphic model. So as to why it is called potential function, well, I don't know. It's just called some potential. It's just called potential function.
So how about a random variable does not belong to any maximum cliques?
Then itself is a maximum clique.
Okay.
Any other question? This is called potential function, so which I believe is coming from the statistical physics literature. Anyone may have a question at this point? So basically, we define a function over each maximum clique. You enumerate all possible maximum cliques in your graph, and for each graph, you assign a potential function. And then you multiply them together, you normalize it, you get the probability distribution. And the normalizer, here we denote it by Z, is just a summation over all configurations of X and for the product of the potential functions, right? So it's also called partition function. So we have learned this term before, right? When we talk about the exponential family, we have potential function. Potential function usually means like normalizer. So in this definition comes from the statistical physics literature. So why is it called potential function? Why is it called energy? In early research of the statistical physics, consider like you have like big tank or some like container, right? And there are a lot of molecules. Those molecules they are moving fast. You can imagine for each molecule you have some random variable x to indicate its states, which may include, say, potential position or velocity. Right? That means we have associated like potential energy and kinetic energy. And then, if we consider the whole tank or whole container as one system, how do we determine the status of this system? we can use the states of all the molecules, right? And because those molecules are moving so fast, and it's not possible to observe each one of them. So that's why it's called statistical physics. We want to model the states of the whole system, meaning the states of all the molecules as some distribution. How can we define this distribution? We define potential function. And for each, well, this could be a set of molecules, or could be a single molecules, that the potential function is defined as exponential to the power of minus energy of Xe. So energy could include like a potential energy or kinetic energy, or in some special case. I mean, in a more general case, you should divide it by some temperature, meaning that on average what's the status of your system. So basically, that's where this formulation comes from. But in our case, we do not care about the physical meanings of this. For us, this is just how we define this energy function, which could be any log likelihood. Right? So again, take a look at one example called image denoise problem. So this is the ground truth. So suppose this is the image, and we have like pixels just showing this base theorem. When we observe it, they are corrupted by some random noise. A lot of like blue dots, right? Now our task is to recover the ground truth, or in ours to remove those noise dots as many as possible. How can we do that? We can build a Markov random field. Each pixel will have a random variable. This random variable value represents the ground truth pixel value, but it is associated with observed corrupted pixel value, which are those things, right? So each pixel are connected to the neighboring pixels. So imagine like you have this pixel, right? So you have pixel here, pixel here, pixel here. The neighboring pixels are connecting to each other. That's how we build up our undirected graphic model. Then we can define the energy function. Because this is a Markov random field or undirected graphic model, our probability distribution will define on the potential functions over each maximum clique. The maximum clique will be an edge, will be each edge. Okay? So that's a pair of x and y. X is actually a pair of xi and xj. Right? Y is a corresponding noisy observations. So a commonly used definition is first a summation over the true pixel values and weighted by h, and minus the product of the neighboring pixel values xi, xj, weighted by a second weight beta, and then subtracted by the product between your ground truth value xi and observed noise version, and weighted by a third feature beta. And through this energy function, we can define the potential function, right, which is exponential to the minus energy function, right? And then you multiply them together.
In order to use Markov random fields here, do you have to know the ground truth?
No. We want to estimate the ground truth from the data. Remember, xi here, see, this is x1, x2, x3, x4, are all unknown random variables. What you observe, those shaded circles, which represent the noisy pixels. So given this data, given this graphic model, we want to estimate the values of x1, x2, x3, x4. This is our task. But before we do this, we need to specify how the drawn distribution of x1, x2, x3, x4 are corresponding to y1, y2, y3, and y4, right? That's how we specify the energy function here. Everybody's comfortable, right? Okay, so now you define the potential function as exponential to the negative energy function. You multiply all the potential functions together, you end up with your drawn probability of x and y. Remember, only y are observed. X is unknown, right? And also the parameters h, beta, and eta are unknown as well. So one problem is that we just want to find the map estimation of p, x, y. Y is known, right? Y is observed, and x is unknown. Also, h, beta, and eta are known. We try to maximize the likelihood to find the true value of x and those weights. That's one way, right? Of course, purely Bayesian guy will want to calculate the posterior distribution of x given y. But in this case, let's just consider the simple map estimation. We just want to maximize this drawn probability to find out the optimal value of x and also the parameters here. And this optimization turns out to be very hard. Why? Because x is binary variable. In binary variable, that means you have n pixels, you have 2 to the n status. So it's a combinatorial search problem. It's very hard. A simple algorithm called ICM, which is quite famous, but we won't have time to explain details here, can give you this result. So this time already reduced a lot of noises. If I'm not wrong, I think it has reduced 90% of noise, but still quite noisy, right? And there are more advanced version of this algorithm which can reduce 99% of noises, which are quite close to the ground truth. But just to give you a sense, after denoise, these are the estimated x values. You end up with this.
So in the energy equation, is xj observed?
No, actually it's not observed.
That is also unknown.
Unknown. So what you know is just y. All the others are unknown, including h, x1, x2, x3, x4, and also these parameters h, beta, and eta. They are all unknown. The question is that how can we estimate them from the data, namely those y values? Does it make sense?
So then the energy doesn't. So that's why you need the formula for the Markov random field to convert the energy into an actual probability.
Yeah. An energy function actually you can define arbitrarily. You can define whatever energy function you want. And why people choose this way? You can think of it, right? You have a question? Okay. So first, the individual elements, the values, take into account, right? And second, x and y. So if you do this summation, right? If you expand it, you can consider as an inner product, represent a kind of similarity, right? So that means, okay, your latent random variables, its values must be similar to the observations, although it's noisy in some degree, right? And also, this product of the neighbor should be similar. Why? Because they are neighboring to each other. So you can imagine that if xi is 0, xj will likely be 0 as well, unless in a very strong situation. That's why people usually choose the form like this. But you can definitely define even higher order term, you define your graph like this. So your maximum clique will be a triangle. Connect every three different pixels. Then you can define a larger undirected graphical model, and you have higher order terms like x1, 2, 3. You want those three variables their true values are similar to each other. You can define as well. But here we just give the simplest case. Any question? So now, we have discussed the directed graphing models. They are like Bayesian networks, and undirected graphing models, they are Markov random fields, right? So an interesting question is that can we convert one type of graphing model to another type of graphing model? So here we'll really discuss how to convert a directed graphing model to an undirected graphing model. And usually, if you want to convert an undirected graphing model to a directed graphing model, it's much harder. But if you convert a Bayesian network into a Markov random field, it is very straightforward. So how can we do that? Consider a Bayesian network which is a chain of nodes x1, x2 to xn minus 1, xn, right? So x1 connects to x2, x2 connects to x3, and until xn minus 1 connects to xn. If you write down the joint probability, is p of x1, right? And the p of x2 given x1, p of x3 given x2, and you multiply them until p of xn given x minus 1. Now, if you want to remove the directionality, if you want to convert it into an undirected graphing model, let us just first preserve the original structure, just removing the directionality. Then we need to define the potential function over each maximum clique, right? So the maximum clique here in the chain structure is just the edges, right? Pairwise edges. And how can we define it? So first, for the potential energy over the first maximum clique x1, x2, we need to define the potential energy x1, x2. How can we correspond to the original joint probability? We're just looking into the terms which are contained in x1, x2, right? These only include p of x1 and p of x2 given x1, right? So that means, okay, your first potential function is p of x1 times p of x2 given x1. Okay? And similarly, for the second maximum clique, the x2 and x3, if you want to define the potential function, we just find out the conditional terms in the original probability, which are included in the set x2 and x3, which only includes one term, p of x3 given x2, right? So you can do it again and again until for the last maximum clique, which connects xn minus 1, xn, right? And the potential function will correspond to the conditional term p of xn given xn minus 1. Thus, then we finish our computation. We finish our conversion. So now I want to ask a question: what is the partition function z? What is z?
Be the sum of all those?
Yeah, 1, right? Remember, because we construct our Markov random field directly from the joint probability, right? Z is calculated by summing over this product, right? That means you're summing over this. That means you're summing over the joint probability. It's just 1. But in general, we won't construct a probability directly from construct a potential function directly from another joint probability. Right? You can define whatever potential function, which could be 100 times x squared, whatever, right? And then you need to do normalization. But if you just convert a Bayesian network to the Markov random field, the conversion comes from the joint probability. So your z must be 1 because the marginalization of your joint probability is 1. But in general, we not only need to preserve the original structure of the Bayesian network, removing the directionality, we also need to add extra edges. Why? We can consider a simple graphing model, like only have 4 variables, x1, x2, x3, and x4, right? So when we convert this Bayesian network into a Markov random field, okay, the first step is that we just remove the directionality. That means these 3 edges are just undirected edges, right? But from the drawing probability, we have this term, P of x4, conditioned on x1, 2, and 3, right? So that means x1, 2, 3, and 4 are coupled in one term. So they must be inside a potential function, right? A potential function can only be defined on maximum clique or cliques. That means you have to ensure x1, 2, 3, 4 are connected to each other. So I have to add more edges. x1, x2, x2, x3, x1, x3. That end up with this. This procedure is called moralization. Or in other words, marrying pairs. Because you need to ensure that your definition of the undirected graphic model is valid. You must connect all the orthogonal parents together to ensure that, okay, this conditional, because this conditional term means that all the variables in this conditional term must be inside one clique, right? That means you have to connect all the nodes together. All the parents will connect to their children, but between parents, there might not be edges. You need to connect them. This is called moralization. And then if you convert them, you have P of x1, P of x2, P of x3, and this conditional probability of x4 given 1 to 3, you're absorbed together into this large potential function. Because they are defined on this maximum clique. So one thing we should be aware is that although, like for any Bayesian network, directed graph, we can convert it into an undirected graphic model by moralization. That does not mean that the two types of graphic models have like equivalent representation power. It's actually their representation capability are kind of non-overlapping. That means, like, more precisely speaking, that means, okay, I cannot ensure that for any Bayesian network, all its properties can be reflected by some Markov random field, and vice versa. For any, we cannot guarantee that for any undirected graphic model, we can find a totally equivalent Bayesian network. To see an instance, if you look at this head-to-head case, these 3 random variables, right? This head-to-head case, we know that condition on nothing A and B are independent, but condition on C, they are not independent. You cannot find any Markov random field which can express this conditional independence problem. You can try that. And probably it will be in homework 3. And on the other side, this is a like special undirected graphic model, special Markov random field, right? So it has a very interesting property that first, when A and B are conditional on nothing, they're dependent. They're dependent because there are 2 paths from A to B, right? They're conditional on nothing. That means they're connected. So basically, condition on nothing A and B are dependent. And given C and D observed, A and B are conditionally dependent. And given A and B observed, C and D are conditionally dependent. So again, it's kind of symmetric, right? It's kind of like XOR operation, whatever. To me, it sounds like that. And for this special Markov random field, you cannot find any Bayesian network such that it reflects the same set of conditional independence properties. That would be another problem. Any questions so far?
So for the Bayesian network, you talked about how the direction of the arrows represents the order of the sampling in some sense.
Yeah.
Like, how does the order of the sampling go on in like?
No, there's no obvious.
There's no order.
There's no.
So everything.
Everything like you can consider as joint sampling. If you want to specify like a sampling procedure, you need to look into the factorization of your potential functions. There won't be like a general process as clear as Bayesian network.
Right. Okay.
Yeah, that's a very good question. That's a like difference between the undirected graphic model and directed graphic model. Because using undirected graphic model is always very convenient, but you have to sacrifice some good properties. Any other question? Okay, so now we have introduced the basic properties of probabilistic graphic models. How do we construct directed graphic models, which are Bayesian networks? How do we construct undirected graphic models, which are Markov random fields? And what do you need to know? How to convert a Bayesian network to a Markov random field? It's called normalization. Simply connecting all the pairs for each node. And remember, Bayesian network is an acyclic directed graph, and we have illustrated why according to Bayes rule. Bayes rule also illustrates a sampling procedure. Once you sample one random variable, it can only be conditioned to sample a different random variable. It cannot be conditioned. It cannot be sampled again. And that's why it's, the graph structure is acyclic. And what is the concept for conditional independence? And how do we answer any queries about conditional independence? We need to know the three basic structures: head to tail, tail to tail, and head to head. Especially this alt structure head to head, and explain away effect, which is special to Bayesian modeling, and de-separation or baseball algorithm. And also be aware in terms of expressiveness, no one dominance of the other. Okay. So now let us switch to the third topic. So we have introduced the construction of Bayesian networks and Markov random fields, right? Now you have like very powerful tools. You can use either undirected graphs or directed graphs to construct or to design probabilistic models, right? After a model have been proposed, the next question is the computation, right? Suppose like you have a set of random variables in your graphic models are observed. We would like to ask what is the posterior distribution, or what is maximum likelihood, what is the configuration which has the maximum probability for the remaining unobserved random variables. Those can be categorized into one problem. It's called inference problem. So here I want to mention that when you look into, especially like the machine learning papers, you will see like inference, you will see estimation, you will see optimization into maximization. All those words are talking about the same thing. It's about inference. So inference is model estimation. But for Bayesian guys, inference not only means like point estimation. You also need to estimate posterior distributions. So that depends on the context and on implications. So what's the core task in our inference? Given the probabilistic graph models, our final task, our ideal goal is to compute the posterior distribution of one or more subsets of nodes given the observed nodes. Consider you have like large graphic models. You use your software, you use your brainstorming to design such a fancy, elegant models. Now you collect the data, you know some set of the values of random variables. You want to estimate, according to a graphic model, estimate the values of the unobserved random variables. Right? So if you represent this inference procedure in terms of the graphic models, this is the original graphic model. You have x and y, both are random variables, right? And now, after you have collected data, you know you have observed values of y. Then the remaining question is that how can we compute the posterior distribution of x given y? That is conditional probability of x given y, right? So the calculation, like from the very, very original definition, is just following the base rule. So you have a P of y, which is marginalization of the drawn probability, right, over all possible x. And then you can divide the drawn probability by the marginal distribution of y. You get the conditional probability. Right? Because we can always, given the graphic structure, you can always easily evaluate the drawn probability. So the key issue is how to compute the marginal distribution of this known P of y. Right? How to compute this marginalization, the summation. Right? So this is our k-test. So the k-test in the inference is compute the marginal of one or a subset of nodes in your graphic model. So to explain the challenge in our inference test, we can start with a chain model. You have heard about that. This chain model is really referred to as like a hidden market model or market model. Right? So we have a chain of variables x1 to x big N. x1 connects to x2, x2 connects to x3 until xn minus 1 connects to xn. Right? And here we only talk about the undirected graphic models, namely Markov random fields. Why? Because for Bayesian networks, you can use normalization to convert it into a Markov random field. Then all the inference procedures apply. So if you write down the drawn probability of your graphic model, just multiply all the potential functions, right, over the maximum cliques. So it's psi 1, 2, x1, x2, psi 2, 3, x2, x3, until psi n minus 1, n, x, n minus 1, xn, right? And then normalize with some constant z. Suppose each node, x1, x2 to xn, they are discrete and take k states, big k states, right? So each potential, which is a pairwise function, right, is a k by k table, right? Because x1 can take k values, x2 can take k values, so there are possible like k squared possible inputs, and you have a table to encode all the function values. Now, we consider to infer the marginal of the node xn. So compute the marginal probability of xn only. To do that, we need to summation over all the possible values for x1, xn minus 1 to xn plus 1 to x big N, right? And the summon is drawn probability. So this is just marginalization. Right? You marginalize over all the other variables except xn. The question is, how can I compute this? If we directly compute it, what's the computational cost? So first, to evaluate the drawn probability, we need to multiply n minus 1 potential functions, right? So the cost will be n minus 1, big N minus 1. And then we need to summon over all possible cases, right? So how many cases do we have? So x1 can take k states, right? x2 can take k states. xn minus 1 can take k states, and x big N can take k states, right? So there are marginalization over n minus 1 variables. So each variable can take k states. So you'll have like a k to the power of n minus 1. Right? And each summon will take n minus 1 operations to calculate the product. Right? So in total, it will be exponential. It will be proportional to n times this power, k to the power of n minus 1. Right? So what's the issue? It's very costly, right? Very expensive. You can imagine that the computational cost that grows exponentially to the number of the nodes in this chain, right? So the longer the chain, the more it is expensive. You can imagine that you have like 100 nodes chain, you won't be able to compute this marginal distribution with any supercomputer in this universe, right? How can I address this problem? Of course, we cannot use. If we cannot improve this algorithm, like millions of hidden Markov models in spacecraft or in radars, they won't be useful, right? They cannot be used. Right? How can we address this problem? We can look into our computation, right? So remember, we are doing a summation over all possible configurations. So when we configure xn, so xn can take like k possible states, right? When we do the summation, we're going to fix the states in x1, xn minus 1, xn plus 1, xn plus 2 until xn minus x big N minus 1, right? So that means every time we do a summon, when we enumerate the possible values in xn, we do not need to recalculate the potential function over x1, x2, x2, x3 until x n minus 1, right? Why? Because they are the same. So when we fix x1, say, equals to 1, x2 equals to 2, and until x n minus 1 equals to like 3, right? When we enumerate the values of x big N, so 1, 2, 3, 4 to like 100, all the other potential functions values, they are fixed. You do not need to calculate again, right? You can just factorize all of them. You can factor them all and just leaving the summation inside. That's the key trick to save the computation. The computation saving comes from the distributive law, which one we have learned from our junior school. Right? So remember, like consider the case like you have a compute A, B plus AC, right? So A is like those long product, right? And B is like the last potential function, right? You have different configurations of xn, it corresponds to B and C. So when you calculate the summation, it's not necessary to calculate A once, multiply with B, and calculate A once again, multiply with C, right? We just need to calculate A once and take it out, and first sum over B and C. And you multiply A with this summation. That means you only need to calculate A once. The same idea here, right? So when you do the summation, we'll enumerate the values or the configurations of some random variables in one potential function. The values of all other potential functions can be fixed, right? So enumerate, when you do the summation, you do not need to recalculate them again and again because they are the same value. So why not we directly calculate them first and store them? That's the key to reduce the cost. So now let us look at how to reduce it, right? And for now, I'll switch to the whiteboard mode. So we're considering how we utilize the distributive law to save the computation. Right? So then we try to first sum over all the potential functions, and then do the multiplication, rather than first do the multiplication and then do the sum. Right? And from this point, we can consider to partition the summation according to xn. Xn is something we're interested in, right? So we can try to merge the terms with the same set of values before xn and after xn, such that we won't first do the product and do the summation. Inside, we first do summation in the product. How can we merge them? We first look at any variables before xn, right? So these variables are xn minus 1 with xn, they are in the potential function psi n minus 1 n xn minus 1 xn, right? So we can first sum over xn minus 1 with xn fixed. So when you finish the summation, you will end up with a function of, you first sum over psi 1, 2 from here to here. So this is x1, this is x2, this is x3, this is xn minus 1, and this is xn, right? You first sum over this potential function. So it will be psi 1, 2, x1, x2, right? You sum over x1, you will end up with a function of x2, right? Because this is a function of x1, x2, you sum over x1. You end up with function x2. And then you multiply this function of x2 with the second potential function, which is psi 2, 3, x2, x3, right? So it is again like gx2 multiplied with psi x2, x3 is again a function of x2, x3. Then you sum over x2. You end up with a function of x3. Of course, it's not g, right? It could be like g tilde. Now you multiply this function of x3 into the third potential function, which is psi 3, 4, x3 and x4. Right? So you minus again, you get the function of x4, right? You do it again and again until you reach the n minus 1 potential function, which is here. Right? So you sum over x minus 1 again, you end up with a function of xn here. So you see this recursive procedure, right? So you first start with x1, and you sum over psi 1, 2, x1, x2. You end up with some function is x2. You multiply it into the second potential function, you sum over x2. You end up with function of x3. You multiply with the third potential function. You do it again, marginalization again, until you reach the n random variable, and you sum over x n minus 1. You end up with this function, mu alpha function, xn. Right? This is the first part of your chain. And we can apply a similar kind of procedure in the second part. So this is xn, right? So xn plus 1, xn plus 2, until x bigger, right? So this time we do this recursive computation from right to left. So we first sum over the last potential function, which is psi n minus 1 n over xn. So you end up with a function of xn minus 1. Right? Now you multiply it with the second last potential function, which is psi n minus 2, n minus 1, x n minus 2, x n minus 1, right? So you multiply this function with this function, it's still a function of x minus 1 and x minus 2, right? Then you sum over x minus 1, you end up with a function of x minus 2. And you do it again. And finally, you sum to this potential function, which is psi n plus 1, small n plus 1. You sum over x n plus 1, you end up with the function of xn as well. We call it a mu beta function. So it's a function of xn only. Why? Because when you do the summation from the backward, you're eliminating all the variables on the back part. And this is called a forward function because you sum over x1, x2, x3 until xn. You eliminate x1, x2 until x minus 1. Right? this summation, I mean, intuitively can be considered as messages. Why? Because your computation is like, first, to calculate the forward summation, you start with x1, right? You sum over x1, you get some function of x2 only. So you can consider it as some message passed from x1 to x2. Okay? Then you multiply this message with your potential function, you sum over x2 again, then you get some function of x3. You can imagine this send a message from x2 to x3. And do it again until you send the message from xn minus 1 to xn. That's why we call this this summation as a message. So from the forward calculation procedure, we get the forward message mu of alpha xn, right? And similarly, from the backward computation, we get a backward message. And this computation can be further written as a recursive procedure. Why? Because each time when we calculate mu of alpha xn, right? So it is equivalent to calculate the summation over the n minus 1 potential function, which is the psi n minus 1 n x n minus 1 xn, with the summation of all previous variables, right? This all previous variables can be considered as a summation over xn minus 1. Or in other words, the message passed to xn minus 1. So now we can finish this recursion. So mu of alpha xn is equal to the summation over the potential function xn minus 1 xn multiplying with the message to xn minus 1. And similarly, for the backward procedure, you have the similar kind of recursive representation. Mu beta xn, the backward message, is a summation over the potential function n plus 1. This is xn plus 1. This is potential function multiplying with the message which is passed to xn plus 1. Right? Everyone is comfortable? Or is it still abstractive? I think it's pretty straightforward. If you feel like uncomfortable, you can do this summation by yourself. So you can choose the first 5 nodes, you do the summation, everything is clear. But abstractively, you can represent it this way. And then let us look at the boundary case. So at the very beginning, what is the message of x2? Forward message x2. So x2 is the message passes from x1, right? So it is the summation over the first potential function, psi1 to x1, x2, right? But there is no message goes into x1. So you can consider this message just 1. So you end up with the forward message of x2 is just a summation over the first potential function psi1 to x1, right? And similarly, on the other hand, like the backward message for xn minus 1, they are passed from xn to xn minus 1, right? And so it is summation over the last potential function and on xn. Right? Again, there is no extra message sent to xn, so you can consider the message is just 1. So now you have a forward message and backward message on the boundary condition. Then you can use this recursive computation to calculate the forward and backward message for each node. And for xn, the marginal distribution at xn, it is proportional to the product of the forward and backward message. And of course, we need to do the normalization because it's just summation. Right? In general case, those potential function and our conditional probabilities, you have to normalize it. And do the normalization, you just summation over this product on xn. Everyone is comfortable? Uh-huh.
So can you arbitrarily pick which xn you want, or which point in this chain that you start at?
You can start with x2, and then x2 is here, right? And you can calculate x3, mu alpha x3 given mu alpha x2, according to this recursion. Right? And similarly, you can start with mu beta x n minus 1, right? And you can calculate mu beta x n minus 2 according to this recursion. And when you have like mu beta x n minus 2, you can calculate the backward message of mu beta x n minus 3 until mu beta x n minus 4 until mu xn. And similarly for the forward, it's the same thing, right? You have a mu x2, mu x3, mu x4. You just calculate this according to the forward, backward calculation recursion. Does it make sense? Any question? Well, in the control theory, this is like a very classical algorithm, and they have like other names on that, but this is just a special case in graphic model inverse. Okay, I will continue the discussion on Thursday.